All right, let's have a look at some questions from 2023 AAHL exam papers and see how our revision videos have benefited students to prepare for the test. Okay, so without further ado, let's get started. Yeah, I think it was pretty solid paper. I think especially for the last 2 or 3 questions for each paper, 1 and 2, and let's see how our revision videos, the 7 hours long, actually benefited students to prepare that, right? So first of all, the question number 1 was something with the sector, etc. You already know, so it's pretty trivial. So I will move on. Okay, but yeah, for the third one, it's something with the theoretical probability. And for the theoretical probability, there are 2 things for you to prepare, right? There's a one that is accounting. Are you going to use a lattice diagram, Venn diagram, or tree diagram? Those are the things really concern. But there's another one that is often to do with the simultaneous equations, right? So you do not want to work with the conditional probability. You do not want to work with the union. You do not work with the complement. What you love the most is the single event or the intersection. We love them. So how do we convert them around was the essence that I have mentioned in our revision videos. Okay, and also finding the area with the integration by substitution. For that one, it's just typical substitution with x squared plus 2. That's okay, but I'm just showing that it's quite similar to what we actually have done with the definite integration by substitution, right? Oh yeah, and I think this question was very lovely, right? So because it was actually deriving the arithmetic sequence, finding the pattern of the cup of the area here, which is given by this strange cosine function with square root of x inside. But it was definitely doable. I think the part A was the most difficult one. But as you see, they have asked you to use a substitution. But in our revision video, we also said it's probably better to substitute whatever that's inside. And for part A, it didn't really just stop from the substitution, but it actually extended by parts, right? So that was typical one. But I'm just showing you from the revision video, we actually saw some similar. And yeah, another one with the finding the line intersection. And for that problem here, if you just have to verify, my friend, you don't have to actually do the row reduction. If you just have to verify, you want to show that position vector lies on the plane, and also that direction vector of the line intersection is perpendicular to the normal the plane. So what you do typically is to find the normal vector. For the first plane, for example, I got 2, -1, and 2. If you perform the dot product, hopefully we get to see that it's going to become 0. So that means you verify that it is a correct direction vector of the line intersection, right? And yeah, so that's as you can see, we have seen it already from the revision video that you benefit a lot. And let's have a look at the second one. Let's have a look at the next one. Look at this. Look at this. You already have seen those problems. That's the essence that I want to point out in our revision video, because it's very accurate. You see, often people say, oh, maybe it's too much work. Maybe I shouldn't do it as much because it's just very tedious to work with all those terms. And because in this exam, the questions appear to be quite easy, so I don't have to do all this extensive algebra. But in our revision video, we always warn students that you actually have to do those algebra. You actually have to do this challenging problem. This optimization problem, especially from the exercise from many textbooks, is actually known as quite difficult because it involves a lot of differentiation. But we actually covered in our revision video. And as you can see, finding the stationary point of that was also, it's very similar to the actual exam question. So that's actually really great to show you the point that our revision video is very good. Yeah, and then also what I've also pointed out is that like the derivative of a cosecant, secant, cotangent, the base of a with of the exponent log, we should really try them, right? It's not uncommon to see those problems. We don't get always pretty derivatives, because for this May 2023 exam, what you actually have to do is to extensively work with the derivative of a secant and cosecant. Not only that, you actually had to work with the second derivative. So you actually had to differentiate many times, right? And if you look at the second part of the question B, you see that we actually had to verify that the arctangent 2, it becomes a stationary point. So you actually have to put that in, right, on the first or second derivative. So this optimization problem was done by the second derivative test to verify whether it's maximum minimum. minimum. But yes, it is very important that you are able to work with the composition between the function and inverse trig function, especially something like the arctangent compositing with the secant or cosecant. You have to practice them. It's very, very important. In the revision video, yes, I pointed out that you shouldn't skip those algebra because you should actively engage in with this comprehensive work. Okay, and yes, another very lovely problem. So I was talking about the paper 3 from a school with the polynomial, and then especially working with the fundamental theorem of algebra and how we can describe the reciprocal roots of the polynomial. I think it's very similar to actually the question number 11 from the exam, right? So I just wanted to show you that the revision video, it already presents many extensive questions, and it's actually a shortened version of what I usually teach, and it's a 7-hour long, and in there we have everything that you need to prepare for the test. So I encourage you to actually watch them. But just some video clips that I took to reflect, to show you the similarity between the actual exam and what we okay. So but without further ado, let's actually get into some more interesting problems and see how we can solve them. Okay, so let's have a look at how we can solve them. So for the question number 8, what it was really involving was working with a bunch of trigonometric equation, right? So for showing the first part that the this equation can exist is by letting this to be intersecting. So what we got to do is to let the equation to be the same. But whenever you're working with the trigonometric equation, what I recommend is you always try to convert into more familiar terms such as a cosine and sine. So my best advice is for you to convert the tangent as a sine over cosine. Then we can get this form right away here, and for the rational form to be 0, we want to take on the numerator being 0, and that's what we have. And for the second part here, we want to show that they intersect at the right angle for the gradient of a tangent. So that means that the product of those equations of the tangent, the product of the gradient of the tangents must be the -1 for them to be the perpendicular. So what you do is to find the gradient of tangent first by differentiating each, and then what you want to do is to show that product becomes -1, but at the x equal to k. I didn't bother to write the k here, but you should have written the x as a k. But if you look at the product, it becomes like such. But then what we have established before, the sine x was a cosine square. So I can actually, replace them as a 1 over sine, and hence the product will become -1. Okay, so that's great. And then let's have a look at the value of the sine when they are intersecting, right? So what you want to do here, every time you solve a trig equation, if it's possible, try to work with just the one trig ratio. Here we can use the Pythagorean identity, put it in such, but unfortunately it's not factorizable, so you can use actually the quadratic formula. But I want you to realize that since my domain was from 0 to pi to every trig ratio, sine, cosine, tangent, they're all positive, so we have to choose the 1 plus √5/2. The reason we cannot choose them is because it's a negative value, and in this given domain, it's everything has to be positive. Okay, for this is a very nice vector problem. It's talking about the sum of vectors. For the sum of vectors, please consider that this is really just largely to work with the diagonals of parallelogram. Here we want to describe the OM in terms of A and C. So OM is a diagonal parallelogram of such. So what you have to do is simply just add the OA and AM, and for that we are given as A plus K, A vector A plus vector KC. And MC is just going to be the diagonal of this parallelogram here. So what you want to do is to add this vector and that is just the opposite direction of the A. Remember, vector is a free vector. Location does not matter. As long as you have the magnitude and the direction, you can put him anywhere. So for this one, it's going to be -A. Yeah, so that's how we can simplify him. But every time we got a simple common vector, please group them by. So it's going to be, what is it? 1 minus k c vector. Is how we can also write for that first term. Okay, so for the next part, what we have to show is this nice algebraic form where is something with 0 is to largely associate with the perpendicular of the vectors, because you want to show their dot product being 0. So even though they didn't ask you to use the dot product, we know, since it indicates so beautifully on the diagram that it's got something with the right angle triangle, and you just got the OM and MC vector, right? Hence, it's very tempting to use the dot product. And yes, as if you do the dot product here and then follow all the algebra accordingly, you can see that it's actually going to end up showing the identity that we wanted to show. So the point here is you should try them yourself, but then the thing is you should smell what the question is asking. Here it asks me to define ONMC in the visual, in the diagram. It's got the perpendicular, very likely that it's something with the dot product. Okay, so make sure you're willing to use those information. Okay, so very nice optimization problem, right? So I really want you to delve into by yourself. But here, what they have asked me to do is to express the y in terms of x, and we got the circle equation. Even though the conic section is not in the syllabus, is very popular questions to be asked. So if you got some time, try to revise yourself about the conic section, either up to from parabola, circle, ellipse, and hyperbola. And because hyperbola tends to be quite popular for paper 3 problems as well, so it's good to know. But anyways, yes, for this one we're gonna rearrange, but then because my q coordinate is in the positive, so I'm gonna take the positive in the front. Okay, so that's great. And then for the area, it is a base times height, so I'm going to choose 2y as my base, and the height as I'm just looking at the length, so I don't care about the negative sign. That's the location. I'm talking about just the length. This is gonna be positive 3, and then the x. So that's what we have. But I need to describe things in terms of x for the optimization problem. Just one variable, please. And for that, I can use the substitution of y that we have derived from the previous part. So then the equation is going to be given as such. And this is my point. In my revision video, I have mentioned tremendous I mentioned quite often that you always have to attain the good level of algebra. So for this one, I'm not just going to differentiate this by product rule, but instead you need to please be able to factorize. Why factorization for the differentiation is important is because you're going to solve it for stationary points. So it's very, very important that we actually factorize. So here the common factor is going to be always preferred with the smaller power. So for example, if you got the x squared, x power 4, obviously we're going to factorize by x squared, right? Because it's got smaller power. So if you have a choice between 1 over root x and then the root x, you should go for the 1 over root x because that's got the power of -half. So I'm going to factorize by 1 over square root of x. So it's going to be 1 minus x. So that's the factorized form. Okay, so that's great. And then, yeah, if you factorize, that's the desired form of the fraction, so that's lovely. And here I wanted to find the maximum area. And for this one, what you have to do is to find the stationary point. And here, as you can see, x equal to -3 would be, either for the numerator to be 0, for the quadratic form is factorizable. So we got 2 stationary points, that's beautiful. But here's the thing, if you want to claim things to be maximum or minimum, you have to verify either by the sign diagram or second derivative test. And for this one, obviously, I don't want to do the second derivative test because it would be very painful to differentiate this quotient rule again with the chain rule. I don't want that. So I like to do the sign diagram. And for this one, as you can see, the denominator is insignificant for changing the sign because it's got the square root outside. It's going to be always remain positive. It's only the numerator that I have to be careful about. And it's a concave down quadratic. And as you can see from the roots, the 3 over 2, it changed from positive to negative, so that means it's going increasing to decreasing for the original function, giving us the maximum. And that, my friend, is how we should do. Okay, that's great. And let's have a look at the next problem. Here is something to do with the complex and the fundamental theorem of algebra. And here's the thing, one of the very common mistake for people to find the argument is that, look at this, tell me what I've done wrong. If I call the argument of that complex number to be theta, it's often the tangent theta is the imaginary part of the real part. So I got the -√3. And if I take the inverse tangent, I get -π/3. And so can I claim the argument to be -π/3? No, because the inverse tangent is an inverse function, it's a one-to-one function. It only gives you one solution. But as you know, tangent is a periodic function. You can have many different angles that will still result in the same value of the -√3. So your best bet to find the correct argument is to draw the Argand diagram and indicate where your complex is. -1 plus √3, it's in the second quadrant, so I gotta find the obtuse angle. So instead of working with -π/3, I'm gonna go with the 2π/3. Okay. So make sure you just quickly sketch. And yeah, and for the real value, that means I gotta have an integer pi for the argument. So the least value that I can do is probably go with the n equal to 3. So if you do so, then you get the straight answer being 8. So that's lovely. And the next question is to work with the fundamental theorem of algebra. And then the thing that I merely want to take is that if for one of our revision video, it says, I think this is one of the paper 3 problem that I mentioned, is that as you can see, uh, preserving the coefficient but changing the order of the polynomial is merely just to substitute with the reciprocal of 1 over w, and then the things can be solved very quickly because you already found the roots from the previous polynomial. What you had to do is just to reciprocate, and as you can see in our video, in our revision video, we actually mentioned. So I don't have to delve into I don't have to delve into too much details of this problem because I want you to solve it. But right now, the purpose of the video is to show you, is to prove how great our revision video was to prepare for your main exam. And for this one, yeah, it's just complex equality. You just have to plug it in the Cartesian form and then compare between the real part and the imaginary part. Compare the real part and imaginary part, and it's good to go. Simultaneous equations, easy peasy, lemon squeezy. Oh yeah, this question also was a very lovely problem, right? So working with the rules of integration, number 1, and then the definite integration by substitution. There's also some understanding with the trigonometric function. So yeah, for this one, it asked me to give to do the substitution, but it was I think harder because it didn't give you the substitution. But you know what? It should be in your blood when you do the integration by substitution. Is always try to work with the substitution inside, within the function. So even though his derivative is not directly multiplied outside, it's very tempting to do the square root of x as a substitution. And if I did, and I try to substitute in everything to replace so that we can express everything in terms of u, you actually realize you got the product of the u and cosine u, which then implies further that you would do integration by parts. So this one doesn't single-handedly solved by the substitution, but it's followed by parts. That's why people struggle a bit here. But if you can actually see the product of u and cosine u, it actually, it's pretty straightforward. So then I encourage you to do the parts on your own, okay? And then, yeah, I like this problem here because it's asking for the x-intercept of the cosine square root of x, right? And for this one, please remember the zeros of a sine and cosine. The zeros of a sine has to be integer pi, and zeros of a cosine has to be pi over 2 plus integer pi. You didn't have to prove it because it was a given, but it would have been nice also, if they actually ask you to derive a sequence for the the roots, and to check whether they know the integer pi or pi over 2 plus integer pi are going to be the zeros of a sine and cosine. But that's how we can solve it here, right? Sure. So if you rearrange, we get that, but it's not the purpose of it. But all you have to do is just to go to the next term by replacing n as n plus 1, and that was just easy peasy, okay? But for the next one, we had to find the area, right? So of the consecutive zeros. So what we had to do is to use those sequence that we have derived before and then use it on the integral. But since we have already by parts, and it's pretty straightforward to solve. But if you plug those values, you already know these are the zeros of a cosine root x. So this is going to be simply, quickly being 0. So that's fine. Only thing you have to worry about is really putting this sequence on the sign and then put a square root, and you actually derive that. If you actually expand, you got something with the pi over 2. And as you know, rotation by pi over 2 is actually something called a complementary angle, for which, in this case, you can actually quickly convert that into cosine n pi. And then cosine n pi is one of the fanciest notation for the alternating term, -1 to the power of n. If you actually then start working in and plug it in and simplify further on your own, I strongly encourage you do. You actually show that it actually becomes a 4n pi. And then the area of under the consecutive area of the area in the consecutive roots of the function happens to be 4n pi, where it appears to be an arithmetic sequence. How do we know it's an arithmetic sequence? For the positive or integer n, I'm given the linear term of the 4n pi, where the gradient is 4 pi, which is equivalent to the common difference. So we can show that is actually the common difference of 4 pi. And we actually have seen something like that in the exam question 2013 May, which also delves into a very nice trigonometric identities as well as defining the area of the consecutive terms. So if you feel like revising similar question like that, I really strongly encourage you to do it. And it was actually in our revision video, so it's actually quite nice. So please make sure you revise through our revision video before your summative or cumulative. It's very, very helpful. Okay. And nice problem also from the vector, where sometimes what we often have to do is to find the intersection, a line intersection between 2 or 3 planes, and between 2 planes the row reduction can be quite painful. However, in this question is asked you just to verify. For you to do so, you just have to verify the position vector and direction vector. And for me, what I like to do, if I'm given the verifying question, what I like to do is just use the position vector first to check the location. You just have to plug this in and see you get the constant 6. If I put 0 to 4 for my x, y, z, I get 0, minus 2, plus 8. I simply get 6, and that's lovely. That's the position vector. And for the direction vector, if you remember, the direction vector of the line intersection has to be perpendicular to the planes. That means the dot product perpendicular to the normal vector. So what you have to do is to simply check with the direction vector of the line intersection and one of the normal vector from the Cartesian form of the vector plane, which you can get easily from the coefficient. You simply apply the dot product. If it becomes 0, then your direction vector is correct. Okay. And for verification, I wouldn't do the crazy row reduction. I would just simply use these rules. So as you can see, for the verifying, you don't have to actually do the actual work of the row reduction. Simply use position vector, just plug it into the plane, and direction vector, put it into the dot product with the normal vector. Okay, that's great. So I think, and then also, yeah, for finding the shortest distance or vector that gives you that, it's always visualize. It's good to visualize the vector. So this was our line equation. And as you can see from this one, everything with the shortest is really just to work with the the perpendicular. And for a vector with the perpendicular, you smell, yes, the dot product. So what you want to do is to compare the direction vector of the line equation, which was 1, -2, -2, and then dot product with another direction vector between the origin and then the moving point on the line equation that I have to find the point. So here, that's put into the parametric form. All you gotta do is just subtract, right? So then you're doing the dot product of this two, and then call that equal to 0, right? So that would give you the lambda that we need to find the this shortest distance. But also it's good to memorize this formula for finding the shortest distance between point and a plane or point and a line. So if you haven't memorized it, it's not in the booklet. It's very good to memorize it for your either school test or the final exam. Okay. And question number 9 was a very nice combinatorics problem. It's always good to play around. If the problem doesn't become so obvious, it's always good to play around with first few numbers and try to find a pattern. But for this one, it's really just the congruence modulo, right? So it's talking about the divisibility, right? So if we try to find all numbers that are divisible by 3, then yes, adding them up will obviously be divisible by 3. And for the remainder 1 or 2, if you add them, the remainder now becomes 3, then becomes divisible by 3, no problem. Remainder of 1, 1, 1, if you add them together, that becomes 3, so that's great. Remainder 2, 2, 2, if you add them up, that's 6, that's divisible by 3, so that's lovely. So as you can see, we can choose one number that gives a remainder 0, 1, 2 each out of the 10 options, because it goes from 1 to 10, and then you can multiply them together. Or you can choose 3 numbers out of the 10 options that has the remainder of 1, and then adding them together will guarantee that you have the divisible by a number, divisible by 3 for the sum. And also, yeah, it's the same thing goes on. So you just have to work at all those independent cases and then call them as a total number. So it's a very nice, lovely divisibility problems. And yes, another question number 11 here is a very lovely problem. It's a very popular optimization problem. This shape is super popular. super popular. And for N1, you want to use similar triangles. And then here I got the adjacent, and the hypotenuse is very likely to work with the cosine. I got the hypotenuse opposite, very likely to work with the sine. And then as you can see, we actually did this in the revision video, right? So this same shape has been there, so please, use it. Just for me to prove you that this is actually almost telling you the answer before the exam. And yeah, and then one thing that I have to comment here is that this question extensively asks you to use the algebra, so that's very nice, right? So this is why I ask you also. It's very important to memorize this advanced derivative differentiation rules other than sine, cosine, or tangent. Reciprocal trig or exponential log with different base other than e should be memorized also. And here, yeah, you feel comfortable, then secant, tangent, negative cosecant, cotangent will be the derivative, and looking for the stationary point, my friend. As you can see, I'm not a big fan of the reciprocal trigs or cotangent or tangent. I'm more fan of the sine, cosine. So simply just putting everything in terms of sine, cosine gives you some clue. And if I have the equality between the sine and cosine with a constant multiple, it's probably better to divide them by, so that I get the tangent. So now if you put the cube root, I get the tangent alpha is equal to 2, and then the domain, my friend, of the alpha was from 0 to pi of 2, which then puts the value in the first quadrant. That means I will have just one value, that I'm okay to use the inverse tangent. So the alpha is going to be our tangent. It is a stationary point. It doesn't necessarily mean maximum or minimum. It could be a stationary inflection. So what you have to do is to verify maximum or minimum. What was so great about this problem here is that it actually used the second derivative test. The second derivative test on this one seems to be such a painful differentiation, but they actually demanded you to do it, so you should do it. Right? So this is very, very important differentiation rules. And after having done that, make sure you try to do this on your own, also using some product rule and chain rule, but this is going to be then the form. And then what you had to do is actually to use the stationary point and the second derivative to get the value. And for this one, what you also have to remember is to working with the inverse trig with some other ratio, using the Pythagorean identities to convert around. For example, if I have a secant arctangent 2, it's quite unfortunate because I don't have the tangent right away to use the property of function inverse function composition. However, as you know, 1 plus tangent squared theta is equal to secant squared theta. So what we can do is actually to re-express in terms of tangent using the Pythagorean identity, other than sine squared plus cosine squared, right? Again, if I have this composition between the arctangent and cosecant, my job is to convert cosecant into something of a tangent so that I can use the function composition. For that, you remember 1 plus cotangent squared theta is equal to cosecant squared theta. And yes, for that one, we can use the reciprocal tangent as such, and then you use the composition deriving the value. So if you actually plug everything in, you can get the second derivative at the stationary point of the arctangent 2 being 45 over 4 times root 5. So that's lovely. So you now found the stationary point. You now found the second derivative being positive. That means the concave up stationary. That implies that it's going to be local minimum. So we verify that arctangent 2, I'm going to have a local minimum. If you actually plug into the original function, you can get the minimum value. So that's great. And what this question then asks is that whether the 11.25 meters can actually pass through that room. So here, tell me what I've done wrong. I'm going to give you the wrong answer, okay, and explain to me why I'm wrong, okay? So what I've done first is the following. Look at this. This is the minimum value. So if it's a minimum value and I had a turning point, it's going to look like that, right? So I know that my arctangent 2 will give you the 15 root 5 over 4 from something like that of the concave up stationary point. Okay, and then and my length of the pole was is 11.25. But for the comparison, it's probably better to use the fraction. And then it becomes 15 times 3 over 4. So all you got to do is to compare between root 5 and 3. And as you know, root 5 and then the 3 square. Okay, oops, sorry. 3 is bigger, right? Because 3 squared, root 5 squared, becomes 5, and 9, obviously 9 is bigger, so square rooting it would preserve the inequality. So then I know 15 times 3 over 4 is bigger, right? So, and look, my function looked like that, and it said that my 15 times 3 over 4 is bigger, right? Look. So this was a minimum value. And obviously, the value that is bigger than the minimum value would exist in the function. So now I got this value here that is likely to give you the angle. So then can I say, oh, hold on a sec. So in this function, my value is bigger than the minimum, so there must be some angle that gives that length. Hence, I say that it passes. Is it okay to say? In fact, this is not okay to say, because it's not okay to say because what you just did, okay, is actually to find the minimum pathway of the shape. So if I give you an example, so imagine that it's a cave. I'm in the cave. Oops. Imagine I'm in the cave. So in the cave, what I just did for you, okay, is that I found the minimum height of the cave. And my height is actually bigger than the height of the cave. Can I pass through? No, I cannot, right? Because that minimum height actually makes my journey not passable, right? So that's what you're doing. You're not actually getting the minimum length of the pole. You're getting the minimum length of the pathway. So if the object is bigger than the minimum path, you cannot pass through. It has to be actually less than the minimum pathway of that shape or here of the cave. Okay, so no, because it's not smaller than the minimum, we cannot pass through is actually the answer. So very lovely. But point I'm trying to make here is actually describe this extensively in our revision video, the 7-hour long. So what I really encourage you to do is therefore, whenever you have a summative or cumulative, or preparing for the November May exam, no problem. Use that video, delve into the problems on your own, and then try to enhance your understanding. Okay, but yeah, that's pretty much it for me. I just wanted to quickly go over a nice problem from the May 2023 and then tell you how great it was in terms of our preparation for the revision video. But that's pretty much it for me today. I will see you around. Thank you.